Dr. Elie.
You can go ahead and start.
Okay. Hey, my name is Elie Libbos, and I'm going to present today on variable pole induction machines in EVs from a power electronics perspective. So currently, the EV industry is dominated by permanent magnet motors, with the induction machine being also the second dominant motor. So it's kind of a induction machine versus permanent magnet. And the reason permanent magnets are dominant is because they have higher peak efficiency, higher power density. But induction also offers some distinct advantages, such as it's more cost effective and it's more fault tolerant and a rugged motor. And so here, for example, is a machine, is a car Audi e-tron in 2019. It uses 2 induction machines. And there is a push to use more induction machines, basically because people don't want to be, like, if there's a shock in the price or anything of permanent magnet, they don't want to rely more on these materials. So the US Department of Energy is pushing towards using less and less magnets. And inherently, induction machines are magnetless motors, so they don't use any magnet. So what are the characteristics in an EV industry that makes the induction machine a bit weak, and what can we do with variable pole induction machine? So for example, an ideal EV, here's the speed and power for an ideal EV characteristics. And you can see the rated power, which is 1 per unit, must be delivered over a wide operating speed range. While in real life, the induction machine capability drops below the rated capability at high speed, meaning that we can't run it at a really high speed beyond that speed we call base speed. And the reason is not coming from the machine itself, but rather from the power electronics. So what happens is that the inverter voltage, when we increase the speed of the machine, we increase the frequency. But when we increase the frequency, we need to increase the voltage too. But eventually, the voltage feeding the inverter is limited. So we can't increase the voltage indefinitely. And then we'll enter the flux weakening region where our capability drops. Now, on the other hand, the variable pole induction machine overcomes this problem. The reason is, for example, think about this 6-pole design, and the capability is dropping. But at point A, you can switch to a 4-pole configuration and get higher power, basically. At point B, you can switch to a 2-pole configuration, and you can guarantee over a wide speed range, you have a higher power capability than the required 1 per unit. So the way pole changing is done typically, electronically, it's done by adding more power electronics. So it's purely from power, we need more power electronics. And the reason we can do that in an induction machine, again, is there's no magnet. So everything, the pole count in the rotor, will follow the stator excitation. So whatever we excite the pole count in the stator, the rotor will follow it. So we can change the pole in this induction machine. And here another attractive feature of pole changing is that this is the power going from 0 to full load. And in EV application, you don't always run your motor at full load, meaning if a motor has a high peak efficiency but is not very efficient over all loading condition, then we don't want to use that motor. But in here, the variable pole has a really good feature. For example, the 6-pole, the high pole is very efficient near rated conditions. But as our power drops, we can switch to a 4-pole and keep the efficiency higher. And then we can switch to a 2-pole and maintain a high efficiency over all loading conditions. So in here, I'll show you as an example the machine we have in the lab, which was built by Dr. Matthew Miguel. And I'll use this to illustrate how pole changing is typically done and what constrains pole changing. For example, why in a 3-phase drive, if I have 3-phase power electronics, I can't change the pole count. Why do we need more power electronics? And if you look at this machine, the stator of a machine in real life has a discrete number of slots. It's not going to be continuous. For example, this machine had 36 slots. I think you can see all of them in here. And we have external access to all of them. So for example, when we start grouping these slots together, for example, think about slot 1 and slot 2. If I place them in series, then the current going through slot 1 If I know the current going through slot 1, I know the current going through slot 2. So they're not independent from each other. So actually, if I had 36 independent slots and I group 2 slots in series, meaning now that I only have 18 independent currents, so my control freedom decreases. So the more we start stacking them in series, parallel, the more we lose control freedom. And if I want to wire this machine at 3-phase, I would have 12 slots, 12 out of 36 slots in series, meaning that I only have 3 currents to control. The phase A current, phase B, and phase C, and in real life, they must sum to 0. So we actually have only 2 degrees of freedom to control the machine. And in real machines, this, I'm showing that we're stacking them externally, but this could be also done in the winding design. But theoretically, one could think about it as external grouping, but in real life, it may be done in the winding design, not even externally. So here's an example. Imagine, now let me illustrate how pole changing is done. So imagine you have a nine leg drive. So it has 9 terminals coming out of the power electronics, and we have 9 input terminals from the machine side. So imagine my machine, whenever I have 9 phase, this is an assumption, it comes from the winding configuration. Imagine when I have a 9-phase excitation, my machine will operate as 2 poles. So, but as you notice, the 9-phase excitation, we can do one more thing. What we can do is I have 9 phase. I can do 3-3-phase, meaning that I have current I1, current I2, current I3. Then I actually repeat a 3-phase pattern. So in the 9-phase drive, I can do a 3 times repeating pattern. And when you start thinking about repeating pattern, it's like magnetically, North Pole, South Pole. Then we repeat it again, North Pole, South Pole. Then we repeat it again, North Pole, South Pole. And my machine will operate as a 6-pole by changing just the phase number of the 9-phase inverter. Well, if you think about it, if you have a 3-phase inverter, you cannot do that. If you repeat 3 single-phase pattern, you will only get pulsating power, not really constant power that will flip the machine. So that's the degree of freedom that comes from using more power electronics connected to more machine windings. So the outline of the rest of my talk is basically what I did so far is I motivated why we need variable pole induction machines and why do we need more power electronics to be able to change the pole count. But how does that affect the power electronics design in terms of efficiency? If we get more in terms of machine, what's happening to the power electronics? Are we trading off something? What's really going to happen when we start using more and more power electronic switches? And then I'm going to talk about capacitor sizing, because when you have more than 9-phase, more than 3-phase, there are advantages in terms of capacitor sizing. And at last, I'll present my experimental results. So here is a picture that Professor Banerjee hates, but he's not here. Okay. Okay, so imagine now I have certain number of terminals at the input of my machine. I determine them based on I want to do pole changing. Okay, here's how many terminals I require coming from my machine. The number of power electronics terminals must match it. There's no way. We need to control each of these currents. If I have only 3 terminals of my power electronics and 9 terminals of the machine, then we don't have much freedom because we need to stack the machine terminals together. So the number of power electronics terminals must match exactly the number of machine terminals. And in general, I use that as, I refer to it in the rest of the work as number of inverter legs. And when we start thinking about drives which are more than 3-phase, for example, think about you have an 18-phase drive. The reason I draw it in here as modules, the reason I draw it in here as modules is that if you have, for example, an 18-phase drive, I can build 2 9-phase drives, that forms an 18-phase drive. I can build 6 3-phase drive, this forms an 18-phase drive too, or 3 6-phase drives. So we have much more flexibility, while a 3-phase drive, you cannot divide it into single-phase modules. The one assumption we're going to take for the rest of the work is that the minimum phase in a module is 3-phase, because anything below 3-phase will pulsate the power and is not good from power electronics perspective. So that's why a 3-phase drive cannot be modularized. But once you have more than 3-phase, you can divide it into modules. And basically, when you have several modules, their DC side, they're driven by the same DC bus. So at the end of the day, we need to either series stack them from DC perspective or parallel stack their DC sides. And this has also a design freedom that can be exploited. So basically, what I just said is that we need more number of inverter lag. What that translates to directly, it's more number of power electronics switches. So more number of inverter lag, more number of power electronic switches. So is it feasible? Is it being done in the industry, or is just three-phase being done? Actually, it's being done. Here is the Tesla Model 3 inverter. They use 24 silicon carbide switches. In a conventional three-phase inverter, we use only 6 switches. And here they have 8 switches per phase, which they group together. And the reason, we will see in the next slide the reason why they actually do that. But the reason, they could use one higher rated silicon carbide. It's available on the market, one higher rated that can drive one phase alone. Why do they need to use 8 rather lower rated switches rather than one highly rated switch? But in our work, we will assume if there are, for example, 24 switches and we have 2 switches per inverter lag, we'll have 12 terminals coming out of the machine. Because from pole changing perspective, an induction machine benefits from having these terminals. So if we have more switches, we're not going to group them from power electronics perspective and just have 3-phase terminals. We're going to actually use 12 terminals if we have 24 switches, because the induction machine benefits from having more flexibility. Here is the graph. So we surveyed gallium nitride and silicon carbide devices on the market. Mainly we didn't include silicon because they're much higher efficiency, so then the comparison wouldn't be fair. And what we did was we looked at the kVA rating of a switch. By kVA rating, what I mean is we multiply the voltage rating of that switch by its current rating, and we look at the conduction loss in that particular switch. And what you see here is an increasing trend. So as the kVA rating of a switch increases, the loss in that switch also increases. So this gives us 2 design choices. Okay, now we can either design with a high number of inverter lag, like an 18-phase, 36-phase drive, with a high number of switches, but we have a low rating of a switch and low loss per switch, or we can design like the 3-phase drive with a low number of switches, basically 6 switches, but the switch will require a high rating and a high loss in that switch. So these are 2 design choices we have at this point. And then here we look at the switching energy, which can be directly related to the switching loss, because when your switch actually switches, there's a transient power dissipated in the switch. And the switching energy can be multiplied by the switching frequency to get switching loss, so it directly relates to it. And what you can see is a similar trend, an increasing trend. When you increase the kVA rating, the loss in a switch increases. And actually, if you look at GaN is much more superior. It's following, like it's below the silicon carbide, and it's known because the gallium nitride material can switch very fast compared to silicon, assuming that the package doesn't limit us in this operation. So in here, what we did was we designed a certain inverter, and we selected, okay, I want 3 terminals coming out of the inverter, 6 terminals, 9 terminals, 18 and 36. And we optimized with respect to losses to see, okay, what happens when we start using more inverter lag to the total losses. Now we're not looking at the losses in one switch, we're looking at the total conduction and switching loss and all of the power electronics. And what we see is that the 3-phase is the worst case. And as we go, 18-phase turned out to be the best, and 36 has a bit more losses. Okay, and the reason, I'm going to take a look at some of these designs specifically. For example, this is the 18-lag drive. It uses a silicon carbide switch. And I'm assuming the DC bus voltage is 800 volts, basically based on the trend of EVs. They're going to higher voltage. 800 is a reasonable number based on the targets of the DOE. And the load apparent power is 125 kVA. And what you can see here is that the rating of the switch is like 1.5 times the DC bus voltage. The current rating is 47 amps, but the VA rating is 56.4 kVA. So this is an efficient design. But let's compare it, for example, what happens if we want to use 36 inverter lags. So actually what we do in here is we use this, the voltage rating is roughly divided by 2. You won't find exactly a 600 volt switch on the market, exactly as much as you want, but the current rating is maintained the same. But now the VA rating decreased from 56 kVA to 30 kVA. So the rating of the switch is now smaller. So there's no magic. Either the voltage rating has to decrease or the current rating has to decrease when we use more switches. But in here, what you notice is that the DC bus is 800 volts. It's higher than the rating. How can we achieve that? Because when you have 36 lags, imagine I have 36 leg and my DC bus voltage is 800 volts. What I can do is divide this 36 leg drive into two 18 leg drives and connect its DC side in series. So each module now sees only 400 volts, so we can use the 650 volts. And this is actually becoming a very popular idea because gallium nitride, the rating of commercially available gallium nitride is roughly 650 volts. You can find probably one switch at 900 volts, but most of the rating is at 650 volts. So if you want to use them with an 800 DC bus voltage, you can't do that unless you start thinking about these modular architecture, series stacking of modules to reduce rating and utilize switches, GaN switches, which switch very fast. Now here we're going to look at the three-phase. If you notice the three-phase case, I'm using 1200 volts, which is back to the same rating as the silicon carbide switch, the 18 leg we saw. The kVA rating is 360 kVA of that switch. It's much higher. And basically the current rating is 300 amps. So it's either you have to increase when you use less switches, you have to increase your voltage or current rating. There's no magic that's going to happen. So basically what we notice is that trend that you can decrease your losses when you go to higher number of switching devices. But at the end of the day, the EV application doesn't always operate at the rated conditions. And we were in the previous graph, we were only looking at the rated conditions. But in here, what you see is that the losses for the 3-leg drive is always which is the conventional 3-phase drive, is always higher than all other drives. And the 36 and 18 legs drive are both have the lowest losses. And they're really comparable to each other until 50% loading. And that's because one of them uses gallium nitride, one of them uses silicon carbide. Gallium nitride will be really efficient at light load because it switches very fast. And at light load, switching losses are more dominant than conduction losses, basically. So now basically what we've seen so far is that variable pole induction machines have attractive features in terms of machine perspective, and from power electronics we can design more efficient drives. But one of the big problems currently in EVs they're facing is that in the inverter, filter caps are too big. They take a large size out of the inverter and there's a lot of advantage in reducing the size of these caps. So typically, how do they reduce the size? Is typical way in power electronics is just go to a higher switching frequency, right? And you can reduce the size of these caps. But you can't keep going to higher switching frequency because eventually your switching loss will become much higher, and then motors at high frequency, they have a different model, and there will be basically leakage current and the bearing. So this is not probably too good to go too high in the switching frequency. And the reason it's critical also to reduce the size of these caps is not just, it's more from a power electronics perspective. We want to locate them as close as possible to the switch, and currently their size prevents that from happening, which sometimes causes voltage overshoot, voltage spikes, which are bad for the motor insulation and bad for the switches in the power electronic system. And at the end of the day, we said, okay, these are devices, gallium nitride, silicon carbide, they switch very fast. But if we use them and overshoot the DC bus voltage, then we'll be switching a higher voltage, which will eventually which will be against what we're doing, because we were decreasing switching loss, but now we're switching a higher voltage. So by all means, it is critical to minimize the size of these filter caps. So when I talk about filter cap, just a notation, I club the cap at the input of a module. When I talk about the module, it's not at the DC bus side. I club it at the input of a module. So for example, here are 3 series stacked modules. They can have as much as inverter lag. I didn't specify it at this point. And the cap is located at their input. And the voltage, in voltage ripple, when I talk about voltage ripple, just for definition, I talk about the whole DC bus voltage ripple, not at the ripple for one of the modules, because the whole DC bus voltage ripple is a more fair comparison for all the different architectures, basically. So something I'm going to go back to, which I talked about a bit in the introduction, is the concept of changing poles with changing phase. So it has been already established in the literature that when you use higher phase numbers in power electronics, you can reduce the size of the caps. Basically, capacitors, you can think about it, there's a ripple current that has to flow through the cap. when we use higher number of phases, these ripple currents start canceling each other out, so there's a smaller ripple current going through the cap. But when we change pole count, even this 9-phase drive is not going to always have a phasor 9-phase phasor diagram. We're going to change to a 3-phase phasor diagram repeated 3 times. So that's going to constrain our capacitor size. So actually, because our pole count depends on the phase number, our capacitor size will depend on the pole. So let's see how it's affected by pole. So in here, I'm showing, for example, the 3-phase fixed pole drive. The 3-phase drive cannot change pole count. So the pole count is coming from how the machine is wound, basically. So anyway, we don't change the phase excitation, so which makes sense. Like in real life, it's not supposed to depend at all at the motor pole count. But when we have a higher number of inverter leg, we're going to change the electronic excitation with different pole counts. So that's going to affect our cap sizing. And as you see, the 36-leg drive reduces the cap size by 2.4 times, even at the same switching frequency, without at all increasing the switching frequency. One thing about the 18-leg drive that's very interesting is that for all pole counts, 2, 4, 6, 8, 10, it has a small capacitance, except at this 12 pole. Now, what's happening at this 12 pole? This is the case where where in the 18-phase drive, we repeat 6 times a 3-phase pattern. So it's, again, the 3-phase case constraining us, and it's the same as a conventional 3-phase drive at this point. So if we can avoid this mode of operation, we can reduce our cap tremendously in the 18-leg drive. And in truth, like when you go for an EV application, most motors are 4, 6 poles design, and you're going to go, when you design a motor at 6 pole, you're only going to go to lower pole counts. You may go a bit higher as overload. So I would say the extreme case would be to go to 8 in an EV application. Probably 6 is good enough. So you won't be using this at all, this mode of operation, and it won't constrain your cap size. Now, look at what happens when we so we talked previously in the previous slide. I assumed there's no division into modules. Now, what happens when we divide our caps into modules? So, for example, you see, I kept the 3-phase drive just for reference, and in here, all the remaining 3 drives, all of the 3 drives are 36-leg drives. But 2 of them, one of them is a conventional 36-leg drive, the blue line, I think, yeah, the blue line. Well, one of them, the other one, the orange line, is a 36-leg drive, which is divided into 2 18-leg modules. And you can see when you do parallel division, you can reduce the size of your cap. But that's not really beneficial. We'll see in the next slide. And when you do series stacking, you will see that the cap size increases. What happened? Now we're using, why did the cap size increase? So let me go a bit back to this slide, show you. Imagine I have an 800 volts DC bus, and I want my ripple to be 40 volts. And let's say in here I have only 2 modules. The ripple in the module is 20 volts only, because the ripple is going to add up. So now, because when we series stack them, we need lower ripple in the module, we'll have a higher cap size in that module. But another thing that's very important to remember is that cap, when we series stack 2 modules, that cap is not seeing 800 volts, it's seeing 400 volts, so its voltage is decreasing. And cap size, a more fair comparison would be to look at the half CV squared energy, basically. So when we go to the half CV squared, the energy stored in all caps, it turns out that series and parallel stacking doesn't matter at all, and we're back to the same case where we had an 18-leg drive. The 3-phase drive is still the worst, and the 36-leg drive is still the best. But when we divide the 36-leg drive into 2 18-leg drives, now it's the same as using only one 18-leg drive. So modularization can limit your cap sizing, but series or parallel stacking of module doesn't matter at all if we look at it from energy storage perspective, half CV squared, which is a more fair comparison in terms of cap. So now I'm going to present the experimental losses and the experimental results. So here's our experimental setup. In the lab, we have this 36-slot induction machine with toroidal windings. What we do is we club each 2 slots in series to form an 18-leg. So it has 18 terminals coming out of it, and we have 2 9-phase drives. So two 9-phase drives, so the number of terminals coming out of the drives are 9 and 918, so they match the machine and power electronics match. And they're configured in parallel, their DC bus is configured in parallel, and we have this control board that takes care of all current measurements and generate the PWMs. And basically all pole changing happens in this controller. It's basically just a control command that changes the pole count. So it's electronic, there's no winding change at all. Now here, we'll take a look at the power losses as a function of the number of inverter legs. So I have 18 phase. I could use all 18 phase to drive my motor, right? I could use only one 9-phase unit to drive my motor and group some slots in series for the motor. I can use only three phase out of all of these because I have 18 phase, but I don't need to use them all. We can test what happens when I use 3, 6, 9, 12, 18. But the thing is, in the previous slide when I talked about design, we were using different switches. And here I'm using the same exact switch, so there's no difference in switch rating. But what I wanted to highlight is that in the theoretical analysis, we only considered conduction and switching loss. Now, how will our pattern be affected if we consider the PCB? There are losses in the traces in the PCB, losses in the capacitors, because real components have resistances and so on. And what happens to the trend when we introduce these losses? And in theoretical, only switching and conduction loss are included. So we can see here they follow a similar trend. So these losses won't affect the trend basically, and they follow a similar trend with the number of inverter legs. Now here, what we did, if you remember on one of the first slides, we showed that the machine under partial loading can be much more efficient by using lower pole counts. So in here, I decided to conduct a test in the lab to run the machine at speed of 900 RPM from 0 to 2.1 Newton meter. And basically see what are the losses in the drive when I use 4-pole and what are the losses in the drive when I use 2-pole. As you can see, 2-pole is more efficient under light loads until point A, where 4-pole becomes more efficient. So, in other words, changing pole count not only minimizes the losses in the machine, but also minimizes the losses in the power electronics. And there's a reason for that. Because when you have a certain output power you want to deliver to your machine, if your losses are minimized, then it means you need less input power processed by the less input power at your motor, which will be processed by the power electronics. And if you minimize your current process by the power electronics, you can reduce the losses in these power electronics. So pole changing is beneficial from both the machine perspective and the drive perspective. And here we take a look at the voltage ripple. Because we have the same caps, so in the analysis I showed what happens when we vary the caps for the same voltage ripple, and here we look at what happened basically to the voltage ripple when we use the same caps. And when we operate as 2-pole, which is a 9-phase system, you can see in here the voltage ripple is much smaller compared to the 6-pole 3-phase system, and this ratio is roughly like 2.5 times, it's even more than what we theoretically predicted. So in other words, if I want to maintain the same voltage ripple, and in EVs it's typically 10% of the DC bus voltage, meaning I have to use, for the 6-pole, for the 3-phase case, I have to use a higher, basically a higher capacitance value. So the 3-phase case really limits the capacitor sizings. Whenever you go higher than 3-phase, it's always good to go higher in terms of caps. So the key takeaways from my presentation today is when we have a higher number of inverter legs, basically a higher number of terminals and more power electronics, the induction machine is a flexible machine that can benefit from that. Mainly because we can reduce the losses in the drive, we can reduce the losses in the machine, and we can extend its speed range. And when we design power electronics with more lower rated power electronics, we can achieve more efficient design and shrink the size of our caps. To acknowledge the Granger Center and Poets for the funding, and Dr. Matthew Miguel, who some of you might have met, who built the experimental machine we use. Thank you.
So one of the motivating factors for this is desire to not use permanent magnet machines. Are there any comparable issues, like Are power electronics and all of those switches, do those have any, procurement issues or anything like rare earth magnets, or are those much easier or manufactured locally or whatever?
But let me repeat, see if I understood your question.
Yeah, I didn't phrase the question very well.
So you mean like, is there an issue with manufacturing of power electronics with higher number of phases?
Yeah.
So
is it replacing one bad thing with another bad thing, or are the power electronics actually better than the rare earth magnets? To phrase it much better.
Yeah, okay. So the thing is, it's an EV, one of the main criteria is cost, right? Although the PM machine is more costly, but at the end of the day, it's a cheaper system. That's why they use it. Mm-hmm. But induction machine is much cheaper. If we can push some more cost into the power electronics and make it perform better and see, okay, if my total cost is still lower than PM and we can get closer, of course, probably it's too hard to match PM, but if we can get closer to it, then that's a reasonable from price perspective. From reliability perspective, so from what I've heard from EV manufacturers, they don't care much about reliability because your inverter is like $200, $300, so you can go easily replace it if it breaks, unless they can shut down the car or something. They don't care really about like running it in a fault tolerant operation. You can easily, motors and EV, they're targeting like something like a $300 cost or something like that, even power electronics. So it's easily replaceable. But when you use higher number of switches, you have a higher probability that your switches fail. But basically, when one switch fails in a high phase system, you still have, for example, one phase is out, you still have 17 phases to deliver power. In a 3 phase, if one phase is out, you have 2 phases. So we need to compare more on that aspect to see whether it's actually also, there's actually also improvement from manufacturing and design. Mm-hmm. Any more questions?
So ultimately, you want to use the cap for the 3-phase design only, right?
So what I'm planning to do, so in this case, because I divided it into 2 modules, so I had to size my cap at the 3-phase. But what I favor personally, I think going to even 36 legs or 18 legs, as long as I want to see the cost first. But if I use if I do 18 leg without dividing into modules, or 36 legs while dividing into modules, I can cut down my cap size. So the interesting thing is not just, we don't just cut your cap size, but you also cut the RMS current coming into caps. And a lot of times the RMS current limits the size of the cap and the temperature of operation of that cap. So you can reduce even the losses in your cap, which caps really, wide bandgap semiconductor can operate at 170 degrees C, but caps can operate at 100, something less. So you want to really cut down losses to make them operate closer to the machine for people who care about integrated power electronics and machine designs. Any more questions?
So at higher speed, you're going to increase the number of poles? Decrease.
There's good advantage also because lower fundamental frequency for the same speed.
Yeah.
So basically you're less limited by the voltage at these high speeds. And you're not into deep flux weakening. Because flux weakening is really bad from induction machine perspective, because imagine you have a machine, but the machine has a physical impedance, right? So if you keep increasing the frequency and you don't increase your voltage, eventually you cannot even draw your rated current. So eventually the machine will really, the capability will go down. And for example, I have a backup slide about this. So even if you increase the current rating, then this won't help you achieve this high pole. Because in here, where all of these graphs intersect, even with higher current rating, at this point they'll have the same operating current, because basically of you cannot anymore, because of the voltage, deliver the current needed.
Have you measured the overall system efficiency?
So the motor I have in the lab is really poor efficient. That's why I don't want to compare it. It's like 60%, 70% efficiency, but at the design stage, I'm targeting like next, like at least 95%.
So you're going to build a whole new motor.
Yeah. But it's good. It's a good motor to validate basically the theory.
So with this, you can validate the power electronics. Now, once you have that power electronics, you can build a new motor.
Yeah.
So in your evaluation, you jumped from 9 to 18 to 36 phases. would it be possible to do other ones in the middle? Like, could you do 12, 15 phase?
Yeah, that's so at the end of the day, if your phase, for example, if I have 18 phase, your phase should divide by a multiple of how, for example, if I had let's say a 2-pole 18 phase, if I want to go to 4-pole, it would be a 9 phase. But there's something like, for example, 8-pole would be a 4.5 phase, which is a non-symmetrical phase, but it works, and there's nothing wrong with that. So as north or cripple or something, but in that case, you would unbalance your. So even integer phase system are not a big deal. You can do a lot.
So it needs to be a factor of the number of slots to
Yeah.
be
exactly.
not obnoxious.
Exactly.
Number of poles into number of phases should be 36.
Yeah, number of poles into number of phase into a constant Q should be 36.
That makes sense.
Have you done a dynamic experiment?
So now we're
Go from 0 speed to full speed?
So now we're going to the control part. We want to go see what are the dynamics involved when you change your pole count. Because at the end of the day, imagine you're driving at EV and you change pole, and it suddenly bumps. You don't want that.
But when you change the pole count, the inductance will change. So that might trigger some interesting phenomenon.
Yeah, but the thing is, so Matt did it in his thesis, at least theoretically, not experimentally, and it has been done theoretically, they change in pole and even experimentally in the literature. It's much better than a mechanical gear in a not EV. EVs, they use one reduction gear typically, but in a regular car, you have a mechanical gear transition. Electronic transition will be much better, because your poles are kind of decoupled. So 2-pole is decoupled from 4-pole. So if I switch between the two, basically what I'll be doing is ramping down my flux of 2-pole and ramping up my flux in 4-pole. And in the transition time, I don't want to saturate my machine. I can take a longer time to transition, but transition very smoothly. You won't feel it at all.
Being able to feel a transition might be a feature though.
Yeah.
People like the feel of changing gears. So maybe if you can intentionally make it bad from an engineering perspective, people might enjoy it.
Exactly. My friend told me I like this transition. I hate that it's not there in EVs. So.
For EVs, the combustion engine sound because they're so quiet. They're in the
Yeah, that may be an option. A sports car, maybe people like it. Yeah, another room. Yeah. That'd be good paper. Enjoy you. Okay, thank you.